Okay, now let's welcome Andrei Warkentin, coming up. Okay, and he currently works as a senior principal engineer at Intel Corporation on and he's going to present on multi-ISA firmware compatibility, bringing the RISC-V and IHV ecosystems together.
Thank you. Okay, so that's a very long title for something fairly simple, which is what happens when you bring off-the-shelf PCI Express adapters and RISC-V together. So you take your favorite RISC-V SBC and has a PCI Express slot, and you take your favorite GPU and you plug it in and you turn it on. What do you think is going to happen? Probably not much. So let's get into that. So I'm not going to dwell too much on sort of what today is. We all know what RISC-V systems look like today. They're embedded like SBCs. You cannot build a server with them. You cannot build a PC with them. A single vendor, it's usually a board produced by the same company that does the chip. It's all kind of embedded hardware. You get the devices that are right there. They may have, PCI Express, maybe not. The firmware that they have is, it takes this approach, embedded approach. It's just enough to boot the OS. You can boot it from the SD card. If you're really lucky, maybe it will support USB. Important notion is all the drivers that you need for the board, they're baked into the firmware. And this is where you get things like, well, I have a board and I got a PCI NIC I found, but how do I network boot this thing anyway? So where do we want to go? So I think you will all agree that we want to go to a place where RISC-V based infrastructure is indistinguishable from its competitors, whether those are x86 based machines or ARM based machines. If you were to take one of these machines and put one of your IT buddies on, they shouldn't be able to tell it's a RISC-V machine. They should know exactly how to use it, plug adapters into it, rack it up, turn it on, install an operating system. And the only time they should be able to tell it's a RISC-V machine is when they do uname-a, and oh, look, it's a RISC-V machine, not an x86 machine. Okay. So this future world is what I like to call as a horizontally integrated ecosystem, right? Which is, again, somebody builds the CPU, somebody else builds the motherboard, somebody yet else builds a server, and somebody yet else builds an operating system and ships a solution. All right. So this is well understood how you do these things. There are industry standards. You have expectations around PCI Express connectivity or future technologies like PCle. There are expectations on how operating systems boot. There are expectations on how an operating system is able to the same binary image of an OS is able to boot on any number of machines that look like it, look the same, and adoption of other industry standards like ACPI to describe such hardware to the OS. Okay, so great, we want PCI Express devices to work. What does that mean in principle? What do I do to get an existing NIC, an existing RAID controller, and an existing video card to operate in this wonderful interoperable RISC-V world? So are they going to ship with RISC-V firmware drivers? So what do PCI firmware drivers look like anyway? So some of this may be obviously familiar if you work on this, but long story short, PCI is a discoverable bus, devices are discoverable, and resources are configurable. One of these resources was known as there's a ROM that you can configure to appear in some part of your physical address space. And this ROM, this flash ROM, but not all devices have it, of course, but the ones that do, which are typically NICs, RAID controllers, video adapters, this is fairly well structured. If you go back in time, turn on your PC, the first thing, what do you see? You see a little bit of text from the VGA card, right? That bit of text was printed by a BIOS driver that was loaded from the video card, okay? In the more modern world, there are other images there. Well, not that many images, but you have a UEFI driver that, well, it's native code. It's meant for an x86-64 machine. General life, of UEFI. Now, UEFI is it's firmware, yes, but effectively it is its own little operating system. So here, you have a PCI graphics adapter. Great. So there's the core UEFI kernel, the driver for the PCI Express complex. That is used to access the config space and the resources on the card. There's a PCIe bus driver, which is what enumerated the card, assigned resources to it, and made the physical card visible as a logical PCI device to the rest of the UEFI environment. And it exposes this using this PCI Open Protocol. Protocol is just a UEFI name for an interface, all right? And that is what's actually consumed by a driver. Well, where does the driver is coming from? Well, again, the PCI bus driver, as part of scanning for adapters, will also notice that there are ROM drivers, and will load these ROM drivers if they are available. Sorry, I'm just trying to keep track of time. My phone is, of course, locking. Okay, great. Okay, and so if the image is there, and it's a valid image, this will load, and talk to the card, and then make available a graphics video interface, which is then used by the rest of UEFI to display a graphical console, and that's why you see something on the screen. Well, but I plugged in a card which only had a 64-bit x86 driver, so that wasn't a valid image, nothing got loaded, I'm looking at a black screen. All right, that's not good. So, wait, for those of you who have been around, hasn't this been actually solved in EFI technically? Well, technically, yes. There was something known as the EFI bytecode, which was the solution to this, because EFI was out of the box positioned to be an architecture agnostic firmware. So there is a bytecode VM that was fairly ingenious in its design, in that it let the same image operate on 32-bit firmware or 64-bit firmware, could even operate on a 128-bit firmware if you have one, because the size of the pointer is a runtime operation. It's complicated the compiler design somewhat, but it is. And actually the kind of the de facto UEFI implementation Tiny core comes with an interpreter for that. Okay, so this is available to you, but ta-da, not used by anybody. Now, admittedly, EBC was way ahead of the curve, and at the time when it appeared, there was no problem to be solved in terms of compatibility. The Itanium machines that had those devices, they weren't going to be using any PC-style devices, which were still using PC BIOS, and then later Macs adopted UEFI, and later 64-bit workstations adopted UEFI as well, and again, they were not using any Itanium devices and all this. There was a tooling problem. There was only one compiler available. It only ran on Windows. It was proprietary. It cost money. It's not even available anymore. And, well, you could argue it had a different performance profile because, well, it was interpreted. Okay. All right. Now, but there was so 10 years ago when the ARM folks started figuring out that if you were to build a server or a PC, it really ought to look like the x86 server or PC, they looked back at this and said, well, shouldn't EBC make a comeback? And it didn't. Okay. All right. Okay, so how did the ARM ecosystem solve this problem? Again, pretty ingenious solution. It's an emulation layer that uses bits of the QEMU TCG to run the 64-bit OPROM driver inside UEFI. So problem solved, right? Let's go take it, compile it, bring it to RISC-V, and we're hopefully done. Unfortunately, at least I ran into issues with that approach. I do not work on QEMU. I do not work on TCG. It's fairly complex. It's been growing more complex, with the passing year. Just looked at the code, like, okay, it looked like it was old TCG code. Couldn't figure out where it came from, and maybe it would be an interesting project to backport RISC-V support to 10-year-old QEMU, but I thought that wasn't for me. So what else could you do? And this is where I introduce what I call the multi-arch UEFI package, which is a rewrite of the x86 emulator package. And it does so by adopting the Unicorn engine, which is apparently a well-known library used by security researchers. All it does is it basically wraps the QEMU TCG bits, as a library that you can, build and use in Linux, on Windows, or whatever. And we actually ported this to run in the EFI environment. Okay, so this cleanly abstracts away QEMU. Okay. Yes, it works on RISC-V. Yes, it still works on ARM, ARM64. And it's actually kind of interesting because, I mean, there are some benefits to this, aside from just working on RISC-V. So first of all, we can support running not just x86 OPROMs, but also 64-bit ARM OPROMs. Okay, that's probably fairly gimmicky. There aren't that many devices, again, where the vendor bothered to add the OPROM for 64-bit ARM. Again, more on that later, but that's actually kind of an important point to come back to. As part of developing this, we kind of incidentally developed a bit of a test suite, right, for regression testing some of these aspects. And that's been a useful tool in kind of constrain any behavior and at least being able to document, okay, if your driver does this, it won't ever work, or, don't do this, do that, test different things, okay. So, size-wise, the ARM build is somehow 2/3 of the x86 emulator package, which seems a bit odd because, well, aren't you using more code now? But okay, good. All right, and this is a project that is part of the firmware track in RISE. So this is one of the things, and it's functional, it's usable. You can go to that link, you can use it, you can download. This first image up there is an HDMI screen capture of an ATI AMD Radeon pass-through to QEMU, and so there you go. Okay. Okay, so some more pictures. There's Doom. Everybody runs Doom. There's Doom running on the Raspberry Pi 4. So yes, it does run on 64-bit ARM. Okay, so how it works. It does rely on a feature specific to the Tiano implementation that basically allows foreign binary support. Usually it would just bomb Bob, but the driver implements its interface, says, hey, I can support non-native images. And of course, emulation of images only is interesting if you can go both ways. You can't, it's not just running emulated code and allow it to use native services, it's also allowing the native code to, well, invoke your emulated image. Why? Because the driver is either a graphics driver and you're bit bleeding, or the driver is a network driver and you're doing network booting. Okay. And again, also this, well, it's the thunking of APIs is simple because the API, the EFI API itself is very simple in what it does. It doesn't return any large values, It only uses up to 16 parameters. So, okay. Things could have been more complicated, really. Okay. Okay, so in the little bit of time I have left, it's worthwhile to say that this is good. Let's go validate this in real hardware. This will be a fantastic approach, and in the ARM days, the x86 emulator package actually shipped on real servers you can go and buy. So it's definitely a valid approach, but I believe it is a bit of a hack. It's a short-term solution because, well, the 64-bit x86 ISA, it's not a dead language. It's an ever-moving target. So eventually you'll find out that somebody used AVX in their driver, and poof, your driver doesn't work until you go fix the emulation layer. So, it's a bit unconstrained. And if you think you can convince the IHV vendors to drop in a RISC-V driver in their OPROM, nope, didn't work for ARM. In fact, I only think some of the DPUs may expose like an ARM, a 64-bit ARM network driver, just because but there's really a single vendor. Even the video card drivers still are not available for 64-bit ARM systems. And now you have 4 architectures, RISC-V, ARM, x86, and then Long Arch, which is an indigenous Chinese ISA. And now we're talking about RISC-V 128, so who's going to drop 5 binaries into this thing? No one. Okay, so what are we going to do? So this is where I want your feedback. Are we going to resurrect EBC? Honestly, people kind of make this kind of face like, ooh, EBC, well, isn't that a bad thing? Well, I mean, you seem to enjoy eBPF, in the Linux kernel, so why is EBC bad, okay? So, but there's no tooling. Well, you can write a compiler. There are like smaller open source compilers out there, okay, so we can fix that. But what about performance? Well, if I can JIT x86 code, surely I can JIT EBC. Okay. But then how do you convince IHVs to adopt this? So you're still back at the same problem. Okay, so maybe you can meet the IHVs halfway. Maybe you can say, okay, fine, build x86 code, but can we build a subset of that code? Just constrain you on the instructions you're allowed to use, and it's just a minor variation on an x86 target, maybe have some static checking as well. Yeah, maybe. I think, okay, so your emulator becomes smaller, your testing becomes simpler and all of this, but then what happens when we go on 28-bit? Okay, so, I mean, maybe x86 is gonna go on 28-bit, who knows, but, okay, so we have this other problem. Now, you can deal with that using, sandboxing, you can kind of do bounds buffering, but UEFI is a single address space OS, so if you just want to be able to invoke code and not have to know that's emulated or not, you need to be able to match the bitness and be able to use the native address pointers. Okay, so, and then there's WASM, which again, if you have an allergic reaction for EBC, well, there's WebAssembly, which is not really meant for this use case, but surely you could adapt, to, again, have everything running in a single address space. It doesn't give you any isolation, but whatever. The biggest problem with WASM, though, again, there's WASM 32, there's WASM 64, and if you're going to 128-bit, it's going to, well, all right. So I want your feedback. This is not a RISC-V problem. This is a UEFI problem, which does make it a RISC-V problem, but it's also an ARM problem. It's also an x86 problem. And I think, you can't just come up with a solution. You have to have some buy-in on what that solution could be. So think about it. Give me your feedback. I'll be out in the back by the Ventana booth or whatever, but my email, you'll get it through the site. Feel free to reach out and share your thoughts. Thank you.
Thank you, Andrei, for introduction to the horror of legacy hardware. And some people enjoy horror. It's interesting.
It's not legacy hardware. You can go to the store and buy a graphics card. What are you going to do? It's not legacy. It's today and it's tomorrow.
There's a reason why we cover things up and bury them in the... It's better if we don't know. But anyway, this was a good reason why we know why we don't look at these things. So thanks everyone. I think we're out of time on this one. If it's okay, you can catch him to ask questions. And I believe it's lunchtime, so we'll take our break and enjoy the posters. See you all back here at 1:30 or 2 o'clock. 2 o'clock.